This is ASAP. There are no projects. So this is basically I am simulating what happens the first time you download, you install, and you open ASAP. So what I'm going to do today is to show you how to open this Precomputed project, and we will go through all of them if we have time and see input and output. So to open existing project, you can go on File and click on Open, or you can directly click on this shortcut. So I have the project in this folder as an example project, and I have 14 of them. As you see, the extension is .asap. This is as the extension of the project for this software. And so this project have been saved a few weeks or months ago, and then now we can open them again. I can select all of them at once, so I don't have to open one by one. And I can click on Open. And in a few seconds, all the project will appear on my screen. Oh, okay. This is because I'm in the call, I guess I'm sharing, and always technical problems. So, well, apparently now everything is fine. So now I have all my project loaded. As you can see, they're all completed, so I have access to the analysis, which is not the case if I just initialize a project. For example, I can show you how to initialize a fast project of a molecule like CH. I open the widget, I select the molecule from the database, I click OK. I have a new project here at the bottom, but no analysis, because this project is new. So basically, here are all the projects loaded, and they are completed. So this is, we will go through each of them, or many of them, and see what are the input and output. So the first one, we start with a single point project. In this case, if you enter in parameters, you can see which parameter have been selected for this specific project. So we have, in this case, electronic dose and p-dose, charge, bundle charge, potential, and more functions. Band structure and Fermi surface are disabled because this is a finite system, so those features are not available for finite system. Then I'm not going to go to the detail about what we put in the Siesta parameters or the run widget. We just move directly to the analysis, but you can always enter and see which parameter have been used. I like also to mention that if I change any of these parameter and I click on OK, then there is a warning whether or not I want to keep this change, because if I keep it, the project will reset. Otherwise, we would create an inconsistency between input parameters and results. And if I go then in the analysis, as I said, I can view the input file, the output file. Here in energy sections, I can see the total energy of the system, LUMO, HOMO, Fermi energy, gap, energy of the eigenvalues. So summary of them, of all the energy of your system. Next is density of states. We have actually two sections with density of states because they are calculated using two different methods, but the information is exactly the same. Next one is projected density of states. So I can project on given orbitals or atoms the density of states to see to watch the contribution of the atoms to the total density of states. For example, in this case, I can select nitrogen, add a curve, and see the contribution to that atom, to the total density of states. In the charge section, we have an analysis. We have at our disposal three methods, so Mulliken, Hirschfeld, and Voronoi. And for each atom, we have the corresponding charge. Bundle charge can be viewed in 3D, only in 3D. This can be done by exporting a file in a cube format and opening third-party program, or it can be viewed directly in ASAP. So here is our 3D viewer, and okay, now you see very little, but if I change my ISO value, you see how the charge is basically suddenly appearing in my system. Potential, then you see the potential along like the three major directions, so X, Y, Z. There is even in this case the possibility of viewing this potential in 3D. And here you can play a bit with the with the plot and also show the energy corresponding to the HOMO and LUMO. Finally, we have work functions. So the work function is the energy necessary to extract one electron from my system and put it into vacuum. And this red area here represents exactly the vacuum. I can change it, and if I change it, it will change also the value of the work function. So but this is up to the user, basically, to select it properly. And here can be done as previously along these three directions. And if I set a value, for example, of 5 in this specific case, there is a warning telling that the electrostatic potential has non-negligible variations in the selected vacuum region. So this is basically no good, needs to be lower the value. Okay. Next project that we ship with this app, Precomputed project, is an local density of states project. So this is a project to visualize in 3D the contribution of the density of states in a given range of energy. So in this specific case, we've chosen this system of one water molecule plus OH. And if we go in parameters, we can set up the range of energy that I was mentioning before, in which we calculate the local density of states. In this case, a region of energy, including the LUMO, has been chosen. This can be changed by the user, obviously. Here, there is it's not possible to edit the calculator. This is because this specific project can be seen as a post-processing project of a single point project, so that for consistency, these changes are not allowed. Why we need a single point project before is because we need the density of states to then select the region. So before you perform a single point project, I can do it super fast here. I can select this atom, this molecule, sorry, go in the run widget. I can run locally. It's going to take just a few seconds. As you can see, I didn't have to set up anything, set the potential, basis, set parameters, as I provide this for you. The calculation completed. I go here, I select LDOS, and now I have my LDOS project. And here again, I can choose the energy range. Anyway, let's go back to the already completed project. If I go into the analysis widget, I see a 2D representation of the local density of states. So I can select basically the unit cell vector and the height. And so for each of these parameters, I see basically different local density of states. I can change a bit so it looks better, like this. And I can also decide to see where the atoms are by changing the atom opacity. Anyway, this is the 2D view, but we have also a 3D view, and which is nicer. I prefer it. And in here you see, if I change the ISO values, I see where the density of state is spatially localized in the energy range that I selected before. Okay. Next one is geometry optimization. Geometry optimization is a project that is used basically every time, because every time you need to somehow optimize your geometry, so to find the relaxed structure. And the parameters that can be set for this kind of project are the optimization method, the threshold, the tolerance. So when the total max force will fall below the 0.05, the system will be identified as optimized. Cell also can be optimized. We didn't do this in this project, but this can be done. If we jump directly on analysis, I see the evolution of energy and max force at each step. If you want to create a new project starting from the optimized geometry, then you just click New Project here at the bottom of the stack. Single point project. This is the optimized geometry. We have two projects here of optimized geometry. in our precomputed set, because those two projects are used to perform a NEB calculation. So NEB calculation, Nudge Elastic Bands, is a project that is used in order to characterize reaction path, to calculate the reaction path given an initial and final state. So this can be used to characterize completely chemical reaction. In this specific case, we consider the initial structure as this one. So one oxygen molecule on top of a platinum slab. And as a final structure, the platinum slab with the two with the dissociated molecule on top. So the two oxygen atoms now are not close to each other anymore. And what we did here was to create a NEB, exactly, that, as you can see here, that goes from the initial image, the one in which the two atoms of oxygen are close together, to the last image in which they are completely dissociated. The intermediate steps are calculated initially by a simple extrapolation. And on this extrapolation and on the initial and final image, the NEB algorithm is applied in order to optimize this path and find the energy associated with it. Here there are several options that you can play with, but I'm not going now to look into the detail. If I open the analysis widget, this is what I see. I see the reaction path. So these points are the point, basically the identifying the energy of each image on my path. I can also decide to view the reaction diagram, in which here is explained what is the activation energy and delta E, which values can be found on the bottom left. So I see that there is an activation energy of 0.8 and a difference in energy between initial and final state of minus 0.4 EV in this specific case. So this is a way to understand how likely is a chemical reaction to happen and which barrier needs to be overcome to do for the system to go from one state to another. On the right, then it's possible to generate a second NEB project starting from selected images from the previous one, and also to perform vibration calculations on the transition state, which is very useful to understand if the transition state that I'm seeing in the NEB is a true transition state. This is going to be in the next webinar. We are not going to go into the detail here.